7.1.1, Analyzing Graphs. For this video, we're going to talk about x and y-intercepts, intervals where the graph is increasing or decreasing, maximum, minimum, concavity, and points of inflection. As we go through this, make sure that you are also writing down what I'm writing down and take out your calculator as we practice the calculator steps so that you know how to do it as well. So the first part we're going to look at is increasing and decreasing functions. A function is increasing on an interval if the graph is always rising as you move from left to right. It's decreasing on an interval if the graph falls as you move from left to right, and constant if you have a horizontal line over that interval. Notice we're talking about intervals and not x and y coordinate ordered pairs, so we're going to use the x values to denote these intervals that we have. If I look at this first graph that I have, which is a quadratic function, if I look at my y values as I'm moving from left to right, you can see that they're doing two different things. From that first part, as I get to the minimum, my y values are decreasing. Then from the minimum, if I keep moving right, my y values are increasing. So it's important when you're writing your increasing and decreasing intervals that you're also thinking about if you have any maximum or minimum points, because that's where your intervals are going to be changing. So in this case, I have two different things that I need to write down, and I always want to define if it's increasing or decreasing. And in this case, we start off with decreasing. And so I am decreasing from negative infinity to this minimum value that I have. And again, you always want to use your x coordinate. So that's -5. So decreasing from negative infinity to -5. And then from -5 to an infinity, we are increasing. Notice that I did not use a bracket around my -5 because at that point we are neither increasing nor decreasing, so we can't really include the point in either of the two. So we're going to use a parenthesis for that place where it's the turnover point. Now if I go to this second graph, if I'm looking again from my values, my y values, as I move from left to right on my graph, you can see that your y values are increasing on the entire interval. So we don't actually have a maximum or minimum on this function. It looks like a cubic function. And so it looks like my y values again are increasing. So in this case, we would just say it's increasing on the interval from negative infinity to infinity. And then the last graph that we have is just a horizontal line. So for this last graph, this is just going to be constant on the interval from negative infinity to infinity. So let's look at an example of this function right here. We're going to say what are the intervals of increasing, decreasing, and constant that we have. So again, remember, you're looking at the y values as you move from left to right on your graph. So as I move right, I can see I am decreasing until I get to this x value of 0. So that's the first thing I'm going to write. So decreasing from negative infinity to 0. And then if I keep going, I can see that the next portion that I have is constant from 0 to an x value of 2. And for this, we actually do use brackets because we are constant on that entire interval. So I'm from 0 to 2. And then the last part that I have, I can see that my graph from that x value of 2 to infinity is just increasing. And so for this, I want you guys to practice these two problems that are right here. So bring those to class with you. The next thing we're going to look at is your local maximum and minima, which is just plural for maximum minimum. These are the peaks and values of the functions. They are the turning points for where your graph shifts from increasing to decreasing or vice versa. So again, these are the turning points. So it's important if you need to find those intervals that you look at where your graph is increasing or decreasing, vice versa. So looking at these, I can see I have the peaks here and here, and the valleys here and here. Now, we actually call these local or relative maximum, or we call these local, or relative minimums. The reason that they're called local or relative is because they are not the actual highest parts of our graph, because you can see these arrows here continue on, but relative to the points around them, these are the peaks, or relative to the points around this point here and here, they are the relative minimum. If we had a quadratic graph, such as this is what we would call an absolute minimum, because there's no other parts of our graph that are increasing or decreasing on the other sides. So it is the actual lowest of the graph. If I had maybe a graph that looked something like this point right here, we would say is an absolute maximum, because for this point right here, it's the highest point on the graph. This point here would be a local minimum, and this point right here would be a local maximum, because again, relative to the points around them, they're the highest or the lowest, but they're not the actual highest and lowest of the graph. And for these, because we're talking about maximum and minimum points, note that we are going to use the x and y coordinate for these. So right now, in order to find our maximum and minimum points, we're going to use our calculators to help us. Eventually, when you get into calculus, you use calculus. So the next part we want to talk about is concavity and inflection points. Concavity is used to describe the way the curve bends. So if a piece of the graph function bends up, we say the curve is concave up. If the piece of the graph bends down, we say the curve is concave down. So if you look at this graph over here, you can see that this part of the graph is curving down, so that would be concave down. And if we look at the other side, you can see that it's concave up, so we would say that that portion, again, is concave up. And the place where the concavity changes is called the point of inflection. And so that's something that we're going to have to be able to find on our graph when we analyze these. So for this next one, we're going to do this one together. So we have this function, y equals x to the fourth minus 8x squared. So the first thing you want to do when you're writing these is, in order to find the point of inflection where your concavity is changing, you need to be able to figure out, well, where is the maximum and the minimum point on my graph? So looking here, we can see we have a minimum here, a minimum here, and a maximum up here. So I'm going to go ahead and write those coordinates down. So our maximum's at 0, 0. It looks like our minimum's at -2, -16, and +2, 16. So if I want to find the point of inflection where it's changing, I need to figure out, well, what is the average between these 2 points to figure out what the x value is going to be. So I need to figure out the average between the maximum and the minimum. So I'm just looking at the x values. So we have -2 plus an x value right here for the maximum is 0. And again, to find the average, you divide it by 2. So that gives me -2 over 2, which is -1. So then I know that the point of inflection has an x coordinate of -1. So if I look at -1, now I need to figure out, where is that y coordinate going to be? Looks like it's right here, if you look at your graph, at -7. So if you're not given the equation, you can kind of just eyeball in the graph where it appears to be for the point of inflection. Just go to your x value and then look at your graph. Well, where is -1 on my graph? Right here. But in this case, we were actually given the equation, so I could plug this into my graphing calculator, which I already have in there. So if you plug that into your y1, you can actually hit graph to look at what the graph looks like. And of course, we know, because we already saw it before, I need to change my window, because I'm, of course, have y values that are going down to negative 16. So I'm going to do negative 20 here so I can see a full graph. So you might have to change your window sometime. So now I can see my graph. And if I go to second and trace, I can hit the first one, enter on value. And I want to look at -1 just to see if I got the y value correct. And you can see, yes, -1, -7 is where my point of inflection is because it's in between my maximum and minimum values. So now I can see that my graph from here to here, where it changes its concavity, that would be concave up because the curve is bending upwards. And I need to figure out the next point of inflection before I can figure out where it's concave down. So the next thing we're going to do is look at finding the next point of inflection. So now I'm going to use the maximum and the other minimum on my graph. So I have x equals 0 plus, now we're looking at this point right here, 2 over 2, which gives me 2 over 2, which is just 1. And if I go to the x-coordinate of 1 and go down to my graph, it looks like it's also at -7. So my other point of inflection's at -7 as well. And you could also confirm that using your graphing calculator. And so then when I think about my concavity, I can see the next portion from here to here, which is, again, you're using your point of inflections for concavity, is concave down. And this last portion, the curve is bending upwards, so it is concave up. So we actually have two places where we're concave up, and we have one place where we're concave down. So I just went ahead and wrote my intervals. So again, you use your point of inflections for concavity, so I can see from this portion of my graph, from -infinity to an x value of -1, I am concave up. And then from -1 to 1, I'm concave down. And from 1 to infinity, I'm concave up again. So when you're writing these intervals, you also need to write out concave up and concave down, because otherwise you wouldn't know which portion of the graph you're talking about if you don't write concave up and down. So for the second one, you guys are going to do this graph here. Also practice writing your concavity, so concave up and concave down. And again, in order to do that, you need to find your points of inflection. If there is no point of inflection, then we say the curve is concave up or down on the interval from -infinity to infinity. For example, if we were just to have a quadratic graph, for a quadratic graph, there's only, in this case, one minimum point. So my curve is not going to be changing from concave up or concave down, because you have to have at least two. So we would say this is concave upwards from -infinity to infinity. And again, remember, when you're doing the concavity, you're always going to use your x values in order to do that. So now we're going to put everything together, and we're going to look at this function that we have right here, which is f of x equals -2x cubed plus 6x squared minus x plus 3. So you guys really need to make sure that you get out your calculator and practice along so that you know how to find each of these in your calculator. So if I go to my calculator, y equals, I plug this into my y equals, and then I'm going to go ahead and hit graph, which you should be doing too. I'm going to have to change my window again because I changed on the last graph that we had. So I'm going to go to window and do, actually let's do zoom 6 for now. So that'll give me a good window. Of course, it's kind of hard to tell sometimes what's happening around your max and min values. So I might actually go to my window and change it and look at a y minimum of 0 and then hit graph. Kind of see what's happening. So now I can get a little bit a better look. I can even change the window if I wanted a little bit more. Maybe my x values from -5 to 5. So this is a polynomial function. So and remember, polynomial functions don't have any variables underneath radicals or in the denominator or as exponents. So this is a polynomial of degree 3. Because this is a polynomial of degree 3, that tells me that it's odd and then my leading coefficient is negative. So I know when I'm looking at this graph that I'm looking at full window because my side over on this side to the left is going upwards and the side to the right is going downwards. If you were unsure, you could always zoom in or out to make sure you have a complete viewing window of your graph because that's very important for this. So the first thing that I want to find is my x-intercept. So to find your x-intercept, you can go to second trace and go to 0 because we're looking at the zeros of the function. We're trying to find our x-intercept and hit enter. And we did do this the other year. So you scroll over to the place where you're trying to find the 0. And so left bound means you want something to the left of where the 0 is and then hit enter. And then notice that arrow came up here so that we want to make sure the 0 is in between our arrows. So right bound would have to be below the x-axis. So I'm going to hit right. And I went below the x-axis because you can tell by my y values here, even though I can't see it on my graph, and enter. And then notice that my 0 should be in between these two arrows that you have at the top. So if I hit enter on guess, it's going to tell me that my 0 is at 3, or my x-intercept is at 3, 0. So I can put that on my graph too here. Then I need to figure out my y-intercept. Remember, to find the y-intercept, you're always plugging 0 into your equation for x. So second trace value, number 1, if I plug in an x value 0, it'll show me on my graph where my y value is, and you can see it's at 0, 3. And again, I can put that on my graph. The next thing we want to find is our local maximum and local minimum point. So if I start this first one right here is a minimum value. So using your graphing calculator again, second trace, because we're going to calculate, and we're calculating the minimum, which is number 3. So again, you want to do something to the left of that point and hit enter. And notice that arrow came up here, and then go to the right somewhere and hit enter. And so that minimum should be in between these two arrows that you have. So you just hit enter for guess and it will give you your minimum value. So we're going to write this down to 4 decimal places. So we have 0.0871 and then 2.9570. So now that I have that written down, I can go ahead and go to my maximum. So second trace. And now we're doing number 4, which is maximum. So now I need to scroll over to that maximum point and hit something to the left, enter. And then I need to go to the right side somewhere and hit enter. And notice that my maximum would be in between those two arrows, so I can go ahead and hit enter for guess. And I get my maximum point. And the reason I wrote down my x and my y coordinate here is because of the local minimum and maximum, we are talking about the points, so in ordered pair. So I went ahead and wrote that down again using 4 decimal places. Now I need to use my local max and min to be able to write down my values of where I'm increasing, decreasing on my graph. So we'll go ahead and graph this here in order to get a better idea of what's happening. So we have our x and y intercept and our local maximum and our minimum points graphed already. So I'm just going to go ahead and graph the rest of the function so that it looks like what I had on my calculator. So now I can go ahead and use this to figure out my places where I'm increasing, decreasing, and or constant. I don't have any constant here because there's no horizontal line. But we always use our max and mins to figure out these intervals. And again, you want to figure out where the x value is. So from here to here, I can see that I am decreasing. Then from this maximum x value, or excuse me, minimum x value to the maximum x value, you can see I'm increasing on that portion. And then from the x coordinates to infinity, I would be decreasing. So I have to go ahead and write my intervals for this. So decreasing from negative infinity, again, to my local minimum x value. So I want to use this right here. So 0.0871. And then the next portion, I'm increasing from 0.0871 to now the x coordinate of right here, my maximum, which is 1.9129. And then again, I'm decreasing from 1.9129 to infinity. The next thing I can find in my graph is my point of inflection, because that helps me find my places where I have my concavity. So I'm going to pick a different color, my highlighter here. So to find the point of inflection, it's going to be somewhere in between your max and your min value. So probably somewhere around here, it looks like to me. But just to be sure, we can't just kind of guess. We want to actually figure out what that value is using math. So I take the x coordinate of my maximum and my minimum, and then I can find the average of that to find out where in between would be. And then I can plug that value into my equation to figure out what the y value is. So for the point of inflection, which I always just use POI for, we take again our x values. So we have from our minimum 0.0871 plus our maximum up here, which is 1.9129. I add those together and divide by 2. So I did it on my calculator. You can see I added them together, divide by 2, and I get 2 for that coordinate. So for my point of inflection, I have 2 comma. Now I need to figure out what the y coordinate is. Again, I can use my calculator and just use the graph for that. So if I go to second trace value and hit 1 enter, I can see that looks like it's in between my max and my min value. So the y coordinate here is 6. You could also just actually plug it into your equation, or you could just go ahead and look at the table of your graph and see that it's 1, 6. That works as well. Oops, and I wrote 2 there. So 1, 6, not 2, sorry. Don't know why I wrote 2. 1 is the point of inflection, so 1 comma 6. And you can see then, if we look here, my guesstimate was correct for where I thought my point of inflection was. Now we can use that, of course, to find the places where our graph is concave up or concave down. So for this, I can see from here to my point of inflection here, it looks like my graph is concave up because the curve is bending upwards. So that would be from negative infinity to the x coordinate of my point of inflection, which is 1. So from negative infinity to 1, we're concave up. And that means from 1 to infinity, our curve is bending downward, so concave down. And again, you can just see that by looking at the graph that we have right here. So from here down, it curves down, so concave down. And the next step is to figure out the domain and the range. And we know this from last year, and we've already talked about domain and range this year. So the domain of a polynomial function we know is going to be all real numbers. And the range is also all real numbers. And that concludes our analyzing our graph here. So again, we were able to figure out how to find everything using our help of our graphing calculator. It's just hard because you have to remember that in order to find your intervals where you're increasing or decreasing, you have to use your local max or minimum x values to help you. And to figure out what your concavity is, you first have to find your point of inflection, and then that helps you figure out where you're concave up or concave down. So just kind of keep that in mind as you're graphing these. And sometimes you might have to change the y-scale on your actual graph so that you are showing a complete graph, because if you have a maximum or minimum point and it's at 50, you would actually want to make sure when you're graphing it by hand that you're showing what that value is. So like for instance, if I had a graph that maybe looked something like this, and this value was a y value up to 50, you would want to make sure to graph that. So I know that my domain looks like it's all real numbers, and then my range looks like it's from negative infinity to 50 bracket. So bring this with you to class, and we will continue working on analyzing graphs in class.